Okay, so we are now dealing with parallel AC circuits for the second part, in which in this topic is we will be having a three components involved already, which is the resistance, inductance, capacitance. So what would be their characteristics if in the circuit, if they are all present in the circuit, depending on where is the where branch they are available. So in here, I already provided three cases for this topic, so that in order for us to familiarize and also compare and contrast what would be the differences in terms of the parallel AC circuits. So in our first case here, is we have three impedances given wherein all of them are connected in parallel with each other. So the Z sub 1, Z sub 2, and Z sub 3, they are all connected in parallel. So now in our in we know again that the impedance is it is always equal to, for each impedance, always think that the impedance here, it is R positive negative reactance I or J. So think of it that it is either it could be pure capacitive, pure resistive, pure inductive, or RL in series or RC in series. So it depends on the circuit, or it depends on the problem. So again, our Z here, it is always R plus minus X. Okay. So meaning again that it depends on the problem. If it is a pure resistive, it's possible. If pure capacitive, pure inductive, so that's all. Okay, so based on our circuit in our first case, we have three impedances connected in parallel. So if you observe, this is our AC source or supply voltage. So the current that lives in this voltage supply is our total current. And then the current that this is one node in here. So if the current will flow here, the total supply current will be divided into three, which is I1, I2, and I3. So we have three impedances. They are in parallel, so which means that the voltage drop is for them, for each branch, is equal to the supply voltage. But in a different manner for the current for Z sub 1 is will flow here, and also for Z sub 2. So the current that flows in I sub 1, I sub 2, and I sub 3 are different depending on the value of the impedance in here. So the greater the impedance, the lower the current that will flow in each branch. Okay, so let's have a recap first based on our first case in here. Uh, the reciprocal to get the total impedance of the circuit, since we are using again the basic concept of combination of impedances, same on the circuit one application, but in here is instead of having resistances in DC circuits, but this time we are having a impedances. Now, to get the total impedance, just to use this derived formula, or you could use the other one, the application of the reciprocal formula. Okay, so in here, Z sub a total, or Z, it depends on the problem. So Z is equals to R positive negative X. So it depends on the value for our impedances. So this is our rectangular form. This is our rectangular form, and if you convert it into its polar form, you will get the total impedance, and it's, of course, it's a phase angle. Now, in the impedance again, if it is plus, it is lagging. If negative, leading. So it is different in terms of current naman. If it is minus, it is lagging, and plus, it is leading. Okay, so current. So the phasor form for the current and impedance are different. It's because in lagging, the impedance positive and then phase angle, while in the current, it is negative if it is lagging. So vice versa. Okay. The same here as what I've said a while ago, that the current is if negative, that is lagging. Depends on the value of the given. So in the current relation, as we observe here, the total current is the summation of all the currents in here. But take note that we are already in AC circuit, so you cannot add all the currents here just simply using its magnitude, so it is not possible. Instead, make it think of it that we are dealing with a vector, which means that it is the vector sum of the current. This is the resultant or total current is equal to the vector sum of all current that flows for each branch. Okay, so which means that I sub 1, it is use the rectangular form or the polar form. So here, and I sub 2, again, I sub 2, use the rectangular form. You can add them by using as long as you can add the currents as long as there is a magnitude and direction or its angle. Okay, so take it with that. Do not add only the magnitude. There should be a phase angle involved with each for each current. Now for our voltage relation, we know that in our circuit they are just all connected in parallel with each other, so which means that the voltage drop across to them are equal, depend on the voltage supply. And now, in terms of the power relation, in the power relation, of course, it is the apparent power. The apparent power still it is equal to it is all P plus QJ. Okay, so it is also positive, negative. So it depends if it is capacitive or inductive. Okay, so with this, uh, let me see. Okay, the total power is apparent is equal to the sum of the power drawn in each branch impedance. Again, take note that our S sub 1 it is not the magnitude itself, but it is the vector. Right? So, or use the rectangular form. So S sub 1, use the rectangular form. S sub 2, use the rectangular form or the polar form. Okay, so if you convert this into its polar form, you could get the value, pure value for the impedance. In our second case is we are having here a series parallel circuits, AC circuit. So in our circuit diagram, given this is our uh, supply voltage, and then we have two impedances are which is connected in parallel, and these two parallel connected branches, it is now connected in a series with Z sub 1. Or rather, the Z sub 1 is connected in the combination of the two parallel connected Z sub 2 and Z sub 3. So applying the laws or rules in this type of circuit, the current that lives in the supply voltage is our total current. And then it is the same, the current that will flows in our Z sub 1 is because it is the Z sub 1 is just connected in series with the supply voltage. And then, as the I sub 1 or our total current enters here, the current will be divided for the I sub 2 and I sub 3. And with this, we could say that the voltage drop across Z sub 2 and Z sub 3 are equal. Okay. And then the total impedance to solve for the total impedance. So this is how to solve since this is series. So Z sub 1 is the polar form plus 1 over, so this is the parallel combination of Z sub 2 and Z sub 3. So this is how to solve for our total impedance in this type of circuit. Again, just apply the basic rules of combination of impedances. So not all the time, maybe there are more complicated problems, circuit diagram. So just use the basic rules in combining such impedances. In the current relation, we observe here that the only current that is equal is the total current and our I sub 1. And then to make it have it an equation of I sub 1 or I sub 1, I or I sub 1 is equal to the vector sum of I sub 2 and I sub 3. And for the voltage relation, again, we know that in the circuit, the voltage drop for the two connected in parallel, Z sub 2 and Z sub 3, they are equal. And also, our total voltage is equal to E sub 1 plus E sub 2. So it depends, since E sub 2 and E sub 3 are just equal. So again, the voltage drop now here is, since it is series parallel, so just take note that it is always use the polar form for each voltage drop if possible. Okay, so in here, so depends on the situation. So same also with our power relations. And for our third case impedance, this is what we call the parallel series. Okay, so we have two series connected impedances, and the series connected Z sub 2 and Z sub 3, they are in connected now in parallel with the Z sub 1. So in this type of circuit diagram, our total voltage here, the current that lives in this supply voltage is our total current. And as it enters in this node, it will be divided for the Z sub 1 and in the combination of our Z sub 2 and Z sub 3. And our current for Z sub 2 and Z sub 3, since they are connected in series, they are just equal. Okay, so that's the cases of the three cases, or I think there are a lot more of cases, but somehow if you try to analyze the case number 1 and 2 and 3, you could observe that how to get the total impedance, and then the total power or apparent power, and also the current and voltage for each. So just apply the parallel and series. So it depends on the circuit. Okay, so for our first example in this topic is, we are having now our given is a coil of inductance 159.2 millihertz, and then this is connected in the coil. So which means that in the problem itself, it says that it has a coil of inductance and a resistance. So the coil has an inductance and resistance. And this coil is connected in parallel with a 30 microfarad capacitor. So first again is our first move is we're going to create a circuit diagram. Circuit diagram. So our circuit diagram. So in here, so our supply voltage is 240 volts, and then we have, this is our coil, and then this is our sorry. So in our first example, so the coil it has an inductance and resistance. Okay, so it's okay. So okay, so in our in this one is our Z sub 1 and this is our Z sub 2. Okay, so in our this type of problem, so we know that in our Z sub 1, which is the coil, this is uh R plus X sub L J. Okay, so in the problem, so Z sub 1, let's say that this is the coil, this is what they call this impedance for the coil. So first is we need to get so this is our Z sub 1, we need to get the X sub L, which is equals to 2 pi. Our frequency is 50 hertz. And then our a given inductance is 159.2 times 10 raised to negative 3. So our x sub L is equal. So you could use your calculator. Our Z sub X sub L or inductive reactance is equals to 50.0. Okay. Now, we have also here, so therefore our Z sub 1 is equal to 40 ohms plus 50.01 J. Okay. Next, so this is the coil again. Z sub 1 is the coil, which has an inductance of this and resistance. So now next is for our Z sub 2. For our Z sub 2 is which is the coil is connected in parallel with the microfarad 30 microfarad capacitor. So which means that first we get the X sub C. Our X sub C basically this is just equals to 1 over 2 pi 50 times our capacitor is 30 times 10 raised to negative 6 farad. So our X sub C, so using your calculator is we get a 106.10. This is 106.10 ohms. So therefore, so our Z sub 1 it is on it is a RL circuit. RL circuit Z sub 1 wherein we have a resistance and inductance. So this is an RL, while the Z sub 2 is a pure capacitive. So it involves only with capacitance. So again, this is negative 106.10 J. Okay, so with this, based on our circuit diagram, if we could create it's the current that flows here is our total current. And as the current enters the node here, so it will be divided by the two branches. This is our I sub 1. Our I sub 1 is the current that flows for our coil or Z sub 1, while I sub 2 here is the current that flows for the second branch, Z sub 2, or it's a pure capacitive. So this is the representation based on the problem. Okay, now in our first goal is to solve for the current in the coil, so we could get the coil. So the impedance of our coil is already here. Z sub 1 is 40 plus 50.01 J, and then the voltage drop across them is just we know that our E, which is equals to 240, this equals to our E sub 1 and also equals to our E sub 2. E sub 1 is a voltage drop across our impedance, first impedance, D sub 1 or the coil. D sub 2 is the voltage drop across our pure capacitive branch. Okay, so we know that we could get already the at letter A. So to solve for letter A, to get the current, so we indicate that I sub 1 is the current that flows in the coil or Z sub 1. This is just equal to E sub 1 over Z sub 1. So I am not using, so this is one of the effective method to solve for this kind of problems, to have inconsistent subscript so that you will not be confused. So our E sub 1 is just equal to 240 or equal to the supply voltage. And then our Z sub 1 is already available, which is 40 plus 50.01 J. So our I sub 1, this is just equal to I sub 1 is equals to 2.34 minus 2.95 J. And if you convert this into its polar form using calculator mode, so a 2, 3, from rectangular form to polar form, our answer is 3.75 excess of negative 51.35 degrees. Okay, so letter A, the current of the coil. So our answer is therefore our I sub 1. So this is our 3.75 ampere. That is our I. Wherein our phase angle, this is our phase angle. The phase angle of the coil, the phase angle of the coil or I sub 1, its current is 51.35. Okay, it is 51.35. So it is only it is the direction of the coil, the current for the coil. Now next is letter B, the current in the capacitor and its phase angle also. So in the capacitor, letter B, in our capacitor, we know again that the current in the capacitor that we designate is E sub 2 for our pure capacitive, and then E sub 2 over Z sub 2. And we know that our E sub 2 is, this is equals to 240. So over negative 106.10 J. So our I sub 2 is equals to 2.26 J, or it also in a converting it into its polar form, it is equal to 2.26 of positive 90 degrees. This is 90 degrees. Okay. Okay. Okay, again, in our letter A, the current in the coil is 3.75 and its phase angle is 51.35. The negative sign is an indication that it is lagging. Second, letter B, the current in the capacitor or the current that flows in here, the phase angle is 90 degrees. It's because since it's pure capacitive, which means that it leads 90 degrees with the supply voltage. The current that flows in the capacitor is 2.26. Letter C, what would be the supply current and its phase angle? Now, the supply current is, take note that when you are if you get the supply current I sub 1, is we need first to get the combination of the two, Z sub 1 and Z sub 2, combining these two connected parallel branches. So first we need to get the total impedance. So for letter C, let's solve for our total impedance, which is 1 over 1 over Z sub 1 is 40 plus 50.01 J plus 1 over negative 106.10 J. And using, to solve this in complex mode, so our total impedance is equal to 98.63 of 15.85 degrees. Now, for our current is, this equals to the supply voltage over the total impedance. So therefore, our supply voltage is 240, and then this is 98.63 of 15.85. So therefore, our total current is equal to 2.43 of negative 15.85 degrees. Now, for letter C, let's check the supply current is equal to our supply current is 2.43 ampere, and its direction or phase angle is 15.85 degrees. Negative, it indicates that the letter C, that this circuit is based on our solution. This circuit, the entire circuit, this is lagging. since our total current is negative here. Letter D, the circuit impedance is, we already solved the circuit impedance since it is applicable or one of the parameters in using the to solve for the current. So therefore our D, our total impedance is equals to 9.13, 15.85 ohms. Letter E. Letter A, see the power, what would be our power consumed and apparent power and reactive power. So E, F, and G, so they are just related since we have already we have our current and voltage supply, so we could get easily the apparent power. So E times I. S is what is asked. We have here 240. Our current is 2.43 of conjugate current, which is positive 15.85. So with this, we get our apparent power. Apparent power is this is equals to my solution here is equals to 58.580 584 point, let's say, point 2. So you just use your calculator. Angle of 15.84 degrees. And so this is our apparent power. So if we convert this into its polar form, our rectangular form, this equals to 561.9 plus 159.5 J. So therefore in letter A, so this is our true power and this is our reactive power. Okay, so our actual power is 561.9. Okay, 62, almost there. And then our reactive power is 159 point something. So this is our, and then our apparent power is 584 point something. So this is the example number 1. So as we observed, just create a circuit first and then analyze the current relations, the flow of current, and then apply basic principles of combining the parallel circuits. So this is the solution for example number 1. Okay. So for our second example, if we're going um, to analyze the problem that is just in parallel again, the branch circuit is connected in parallel. So we have a 100 ohm resistance, 150 capacitive reactance, and 90 inductive reactance given. So all the three components are connected in parallel. So to make it more effective, so I hope that you know how to transform given the problem, worded problem to circuit diagram. So we know that in the problem, so this is just our supply voltage. So our first impedance is our Z sub 1 is this is pure it is pure resistive since we have given that 100 ohms. And then our Z sub 2 is uh equal to 150. It's pure sorry. So this is okay, so this is since it is capacitive reactance, so this is negative. And for the last is our inductive reactance. This is our Z sub 3, which is equals to 90 J. So what is asked is the total impedance. So there's no need for the value for the total voltage. So to get the total impedance, combination of the three, is equals to 1 over 100 plus 1 over 150, negative 150 J plus 1 over 90 J. Total impedance is 91.38 of it's 23.96 piece. So therefore, the total impedance is 91.38. Okay, for example number 3, a resistor of 50 ohm and an impedance of 100 plus 50 J are connected in parallel with a circuit parallel across the 220 volt supply. So find the power factor of the circuit. So in this kind of problem, again, let's create first the circuit diagram. Our circuit diagram is so they are just in parallel. Our first impedance is 50 ohm resistor, which is our Z sub 1, which is pure resistive. This is 50 ohms. And for our second impedance, this is it is an impedance given Z sub 2, which is equals to 100 plus 50 J. So our power supply is 220 volts. So what is asked is the power factor, and we know that the power factor is just equal to the cosine theta, right? So if we get the phase angle of the circuit, so we could get the power factor easily. So with this, using only the impedance, our total impedance is a 1 over 1 over 50 plus 1 over 100 plus 50 J. So our impedance in the circuit is equals to 35 plus 5. So 35 plus 5 J. Or in its polar form is equals to 35.355 excess of 8.13 degrees. So we know that the 8.13 degrees is our phase angle. So therefore, our power factor is equals to cosine of 8.13, which is equals to 0.989. So if you observe here, so what would be the indication? Is it leading or lagging? Now, since this is plus here, so we know that if we are going to get the current, basically the current will have a phase angle of negative. Okay, so therefore, since it is plus in the impedance, this is lagging. Lagging. Okay. Now, for our example number 4, so I want you to solve it in your respective houses. So right now, so I will give you the so what is asked in the problem is find the equivalent impedance of a parallel circuit consisting of a 5 on resistance, 5 inductive reactance, and 5 capacitive reactance. So I will give you, let's say this is, I will give you 30 seconds. Okay, so timer. So again, so kindly solve this and then, okay. So try to solve 30 seconds. So later, if let's check, we're going to solve it later. So 17 minutes left. Minutes, seconds pala. So 10 seconds, 5, 4, 3, 2, and 1. Okay, so time's up. So I hope you have there your answer already. So let us solve number 4. So in our example number 4, so this is just a combination of the 3 branches connected in parallel. So if we are going to create a circuit diagram, so this is our Z sub 1, which is our Z sub 1 is pure resistive, which is 5 ohms. Our Z sub 2 is pure inductive, which is our Z sub 2 is equal to 5J, since it is inductive. Now for our Z sub 3 is pure capacitive, so it's negative 5J. Okay, so to solve for this, so our Z total is 1 over 1 over 5 plus 1 over 5J. So plus or minus the same lang, so negative 5J. So overall, this is cancelled. So this will become 0. It's because they are in the same value, but the sign is different. And so therefore, our Z total is equals to 1 over 1 over 5. So simplification, this, our total impedance is equals to 5 ohms without using your calculator. So for our fifth problem, it was stated here that a parallel circuit consists of 5 ohm resistance, 4 ohm inductive reactance, and 2.5 capacitive reactance, and it has a inductive coil of 1 plus 5J impedance. So find the complex impedance. When we say, so what is asked is the total impedance of the circuit. So basically, this is just circuit. So our first impedance, as stated here, so this is our Z sub 1 is this is pure resistive. Our Z sub 2 is equal, so pure inductive, it is 4I. Then our Z sub 3 is pure capacitive, so this is 2.5J, so this is negative. And the last circuit branch is related to 1. Our Z sub 4 is 1 plus 5J. So to get the total impedance is just solve for the combination for all of them. This is 1 over 5 plus 1 over 4J minus 1 over 2.5J plus 1 over 1 plus 5J. So I put the negative sign here, so it's up to you. You could use negative in the denominator, or it's up to you. Plus, negative, or I could simplify its negative here. So overall, our total impedance is equal to 4.065. 4.065 plus 0 0.72. Okay, so that's for our example number 5. So for example number 6, so for example number 6, so please ready your calculator and ball pen. So I want you to answer this, and then later we're going to compare our solution. If you get it, you get the same process or correct solution. So I will give you 2 minutes to solve for this kind of problem. So timer starts for problem number 6. Timer start. So kindly participate. So try to solve it with integrity. So that we could check later if, and then we will try to answer this problem later and compare our solution. Timer starts now. Uh-huh. So this is just a resistor connected in series with a capacitor, and then their combination is connected in parallel with the inductor. So what is asked in the problem is to solve for the resultant current. So just try to solve na lang the total current and also the phase angle, and indicate if is it leading or lagging. So we could uh, try it later. Let's see. So guys, 1 minute and 23 seconds. So try to solve, guys, so that you will not get bored while listening, just listening. So there must be a intervention to have a activity. So 1 minute and 7 seconds. So just use this shortcut method, so you will not consume more time. Or maybe okay. So I think there are some of you are done already. Just wait lang muna, and then we'll compare it later. So no need to send the answer in the chat box. Last 35 seconds. Twenty seconds, guys. Seven seconds. Okay, guys, time's up, guys. So, okay, so let's solve. So I hope you get the answer and using the appropriate solution. Okay, so to solve for our example number 6, our resistor is just connected in series. So it is RL series circuit, series branch. So our Z sub 1, so this is our Z sub 1, our Z sub 2. So this is our circuit diagram. So we know that our Z sub 1 this is RC circuit. The resistor and capacitor is connected in a series. So which means that our Z sub 1 is equal to 5. So first is we need to get our X sub C by using its formula. This is 1 over 2 pi 60 hertz times 442.1 times 10 raised to negative 6. So our X sub C is equal to 6 ohms. Okay, and then so therefore this is negative 6J. For our Z sub 2, since our Z sub 2 is uh Z sub 1, so basically the actual circuit diagram is before combining resistor. Okay, it goes like this. It is ano pala. So ganon. Okay, so this is basically the first circuit diagram. Then the series I combine it. It became Z1, wherein we know Z1. So this is an RC circuit, series circuit. And this is a pure inductive. So which means since it is pure inductive, let's solve for our X sub L, which is equals to 2 pi times 60. Our value for inductor is 21.22 times 10 raised to negative 3. So our X sub L is equal to 8 ohms. Okay, so this is negative 8. It's positive. 8J. Okay, so to get the current, first we need to get the total impedance. Our total impedance, which is equals to 1 over 5 minus 6j plus 1 over 8j. So our total impedance is equal to our 10 total impedance. So 11.036 plus 3.185 J. So to get the current, just use the voltage over impedance. So we know that the voltage here is 120 volts, and then the impedance. So therefore, our impedance is here. Therefore, our current is just a substitute this value in here. Our current is equals to 10.34 angle of, our angle is a negative 18 degrees. 18. Okay, so for our example number 7, so our statement problem, our problem is a coil of 50 ohm resistance and inductance is 150 millihertz. And then we have also uh, 50 microfarad capacitance, and we have a voltage source. So our given, we have the voltage source. It is an equation. So we're going to solve for the equation of the total current, number 7. So in the problem, so we have a coil again. So if we create, its first step is we need to visualize the circuit. So we have a resistance and we have a coil and inductance, sorry. So, and this is a capacitance. So if we transform this into an impedance, uh, our voltage source is 100 of 30 degrees. So our Z sub 1, and then have our Z sub 2. So basically our Z sub 1 is, this is RL circuit, RL series circuit, so we could combine them. So first we need to get our X sub L. We know that our X sub L is 2 pi times, do we have a frequency? Okay, so our frequency is not yet given, but we have an angular velocity. So our frequency is equals to angular velocity over 2 pi. So we have given 307 over 2 pi. So our frequency is 377 over 2 pi. 60. So is 60 hertz. Okay, so 60 hertz times 150 times 10 raised to negative 3. So our X sub L is equals to 56.5. 55. Okay, 55 ohms. So our Z sub 1 is equals to 50 plus indication for inductive 56.55 J. For our Z sub 2, it is pure, as we observe in the circuit diagram based on the problem, it is a pure capacitive, which is, first we need to get our X sub C. Uh, 2 pi 60 hertz. Our capacitance is 50 times 10 raised to negative 6. So therefore, our X sub C, I'm using calculator, it is 53.05. Okay. Now our G sub 2, this is a pure capacitive, so this should be X sub J as C, J negative. So with this, we could get already our current equation later. So our total impedance is not yet. So first is we need to solve for the total impedance. Our total impedance is 1 over 1 over 50 plus 56.55 minus 1 over 53.03J. So our total impedance, this is equals to 56.013 minus 57. J. Okay, so to get the current, this is equals to our supply voltage, which is 100 of 30 degrees. So 100 of 30 degrees is based on the problem level the source equation is given. Over our total impedance is 56.013 minus 57 J. So our total current is 1.25 of 75.5 degrees. So therefore our current is 1.25 sine 377 T plus 75.5 degrees. So this is our correct answer. So that is for our number 7. Okay, so for our set work for today, I will give you 3 minutes to answer this problem. So after answering, you must send your PM, your solution in my BGM1 account, so I could check if your set work answer is correct. So you may start answering now. So in our problem is we have two impedances. So 10 plus 15J, and our second impedance is 6.8J. So they are just connected in parallel, and you're going to solve for the total apparent power, true power, and reactive power. So given that the total current is 15 ampere. So you have 2 minutes and 30 seconds left. So I think it's the most effective here is technique or method is to use the shortcut method. You could get the possible answer with. Last 1 minute and 45 seconds. So this is our last activity for today. So next meeting I will create another video for the remaining examples. So last 1 minute and 10 seconds. Okay, last 55 seconds. So you can, so if you're done already, you can try to send your solutions now in Facebook account. BGM po, 38 seconds. Kindly put your final answer in a box so I could easily check or locate the final answer. Last 20 seconds. 5, 4, and 3, 2, and 1. So I hope that you had sent your answer already. So this will be our last session for video premiere in YouTube. So next meeting we will have another video premiere. So if you have clarification for this subject, for our examples or for this topic, you could send a message to me or drop a comment in the comment section or drop a message in the comment section so I could acknowledge. And also, you could try to PM me if you have concern clarifications for examples or the topic rather. So thank you for attending. So God bless. Stay hydrated, by the way.